Now that we've established how to balance chemical equations and the information content that's represented by chemical equations, let's look at some simple patterns of chemical reactivity. We take a magnesium ribbon and we ignite it. What we'll see is a very bright flame, and at the end of the reaction we end up with ash. Now, if we weigh the magnesium ribbon at the beginning and we weigh the ash at the end, we'll find that the ash weighs more than the magnesium. So mass has been added, right, as a consequence of this chemical change, and the product here is magnesium oxide. It's actually a reaction with oxygen. At the microscopic level, we can represent our magnesium surface as a collection, right, of well-ordered magnesium atoms reacting with molecules of oxygen gas. And where oxygen actually collides with the magnesium surface, we find that the oxygen molecules break and insert on either side of a magnesium atom, right, to give a well-ordered array of oxide anions, O2 minus, and +2 magnesium ions as well. Now there are a number of interesting questions here. For example, why do the molecules of oxygen break, and why do they insert between magnesium atoms? What's driving this? Another question is, why do the magnesium and oxide ions form a well-ordered array, and how does the bonding between magnesium atoms give rise to bulk properties of a metal, whereas when we look at the bonding between magnesium and oxygen, or rather magnesium ions and oxide ions, we end up with properties of a fragile ash that crumbles so easily? These are questions that we will be addressing later on in the course. Another thing that's kind of interesting is that if you look at the relative sizes, right, of the different atoms here, it looks like the magnesium atoms get smaller and the oxygen atoms swell up or get bigger. Well, this we can understand simply from the transfer of electrons from magnesium to the oxygen, right? So if you just think of the atoms as containers for electrons, if you lose electrons, the container gets smaller, and if you add electrons, the container gets bigger. Now finally, if we look at a symbolic representation of this reaction that is a balanced chemical equation, it'll look like this. So we find that our compound, magnesium oxide, is present as a 1-to-1 number ratio of magnesium to oxygen. It's not a molecular compound. If we look at this representation here, we don't see individual molecules, but we definitely see a repeating pattern: magnesium, oxygen, magnesium, oxygen, magnesium, oxygen, etc. So they're present in a 1-to-1 number ratio. We also see that to prepare this material, right, we need a 2-to-1 number ratio of magnesium atoms to oxygen molecules, right? Because every oxygen molecule has 2 oxygen atoms. So in terms of an atom ratio, it's 1-to-1, right? But since oxygen is molecular, we write in our balanced chemical equation magnesium to molecular oxygen in a 2-to-1 number ratio, and we get out 2 formula units of magnesium oxide for every molecule of oxygen consumed. So this reaction is an example of what we call a combination reaction, because we have 2 different substances, magnesium and oxygen, combining together to form one thing, magnesium oxide. When we're counting substances, we're not interested in these stoichiometric coefficients. We're just counting the different types of things that are reacting. So we have 2 things combining to form one thing. Here's some other examples. The reaction between nitrogen and hydrogen to form ammonia, we've already seen that, and is arguably one of the most important chemical reactions to our civilization. This is the dominant way in which we make our fertilizer. Here's another example of a combination reaction. We have molecular bromine as a liquid reacting with gaseous 1-propene to form this dibromopropane. Another pattern is just the opposite of what we just saw. Here's an example of what we call a decomposition reaction, and in this case you have one type of substance that's decomposing to form two or more other substances. If we write this symbolically as a chemical equation, it would look like this, right? Two molecules of water coming together and then decomposing to form two molecules of hydrogen and one of oxygen. So it's a 2 to 2 to 1 ratio. Here's some other examples of decomposition reactions. Calcium carbonate or limestone, when heated in a kiln above 800 degrees Celsius, will drive off carbon dioxide gas, leaving behind what is known as quicklime or calcium oxide. This is a process that was discovered, dates back at least to 4000 BC, and was used by the ancient Egyptians to generate a mortar out of this calcium oxide. If you add water to it, you form calcium hydroxide. It's called quicklime, and the Egyptians used that plaster or mortar to plaster the pyramids. The Romans also used lime mortar extensively in their architecture as well. In this reaction, potassium chlorate decomposes to form potassium chloride and molecular oxygen. Potassium chlorate is a disinfectant. It's also a strong oxidizing agent. It's used as the oxidizing component of rocket propellants. In World War I, it was also used in plastic explosives. They essentially just mix the potassium chlorate with wax to make the explosive. Also, potassium chlorate is a convenient way of chemically storing molecular oxygen when you need it. So to get oxygen up to the space station, as well as to provide oxygen in deep sea submarines, we'll use potassium chlorate and decompose it. It doesn't take much energy to do it. And decompose it to form the molecular oxygen. And then finally, another example of a decomposition reaction is sodium azide will generate molecular nitrogen. And this is used in the automobile industry for our airbags. Shown here is a third type of chemical reaction pattern, that of combustion reactions. Basically, anything that reacts with oxygen is a combustion reaction, particularly if it produces a flame. Just about any hydrocarbon or any organic compound will do this. So in this particular case, we have methane or marsh gas reacting with oxygen to form carbon dioxide and water. We see that the number ratio is 1 to 2 to 1 to 2. And you can compare here, we just have twice the number of entities shown here as what's represented in our chemical equation. Here's another example. This is propane, so this is what we use to light our outdoor barbecue grills, right? Propane plus oxygen, again to form carbon dioxide and water.